This time I would recommend Mr. Chellakumar to initiate the meeting. Chellakumar, can you go ahead and start the meeting?
Yes, sir.
Yeah.
Good evening, sir.
Yes.
On behalf of the Popular Science Lecture branch of Tamil Nadu Science Forum, I extend my warm welcome and National Science Day wishes to you all. This is our 35th lecture since we launched the
Chellakumar to
lecture.
initiate the meeting. Chellakumar, can you go ahead and start the meeting?
Yes, sir.
Yeah.
Then make your video available. We can't see you.
On behalf of the Popular Science Lecture branch of Tamil Nadu Science Forum, I extend my warm welcome and National Science Day wishes to you all. Any problem, sir? Lecture since we launched the lecture.
Chellakumar, can you go ahead and start the meeting?
Yes, sir.
Yeah.
Then make your video available. We can't see you. Hey, why is it echoing? Okay, good.
Echo that, sir.
Yeah,
Yeah.
it's coming again and again. Start again.
Yeah, I think it's someone watching YouTube as well simultaneously.
see.
Yeah.
Should not switch on both.
Okay.
Okay, sir. On behalf of the Popular Science Lecture branch of the Tamil Nadu Science Forum, I extend my warm welcome and National Science Day wishes to you all. This is our 35th lecture since we launched the lecture in June 2018. Since then, we have been able to conduct the lecture periodically without any interruption covering the ongoing researches in higher sciences. Our participants are mainly students, researchers, professors, science activists, and those who got an interest in science but missed to have science as their career. Today's lecture is going to be Himalayan glaciers, science and facts. Particularly, Dr. R. Shankar from IMSc Chennai going to discuss on glaciers and climate change. And Dr. R. Jayangonda Perumal from Central University of Tamil Nadu, Thiruvarur, going to explain the Chamoli disaster. I welcome both of you, sir. A brief introduction about Popular Science Lecture and Tamil Nadu Science Forum shall be given by Dr. Seduraman and the state coordinator for the subcommittee on science propaganda. On behalf of PSL, I welcome Dr. Seduraman, sir. The both speakers shall be introduced by Dr. T.R. Govindarajan, Emeritus Professor, IMSc Chennai, an important leader of Tamil Nadu Science Forum. I welcome you, sir. Both lectures shall be for 45 to 50 minutes and it shall be in English. Also, Dr. R. Jayangonda Perumal accept to speak in bilingual manner, both Tamil and English, as many of our participants are from interior district of Tamil Nadu. After this, we have an hour question answer session. We expect you to ask question related to the speech given by the speaker and do not express your opinion on the subject. Please find the link for the feedback forms. We request you to fill up the feedback forms immediately after the meeting as it will help us to review and improve our activities.
Okay. Can you go ahead and Dr. Seduraman?
Yes, sir.
Yeah.
Okay, start. Good evening, all.
Yes.
Yes.
Yes. The one.
Sethraman?
The 1 minute. 1 minute. 1 minute.
Okay.
Good evening. Today is National Science Day. Tamil Nadu அறிவியல் இயக்கத்தின் சார்பில் பாப்புலர் சயின்ஸ் லெக்சர் ப்ரோக்ராம் விமர்சையாக தொடர்ந்து 35வது நிகழ்வு பல தலைப்புகளில் ஆங்கிலத்திலும் தமிழிலும் பல விஷயங்களில் நாம் கொண்டு வருகிறோம். அந்த அடிப்படையில் ஒரு இந்தியாவில் மட்டுமல்லாமல் சர்வதேச அளவில் உள்ள அறிஞர் பெருமக்களுடைய அறிவியல் சார்ந்த தாக்கத்தை ஏற்படுத்தியிருக்கிறது. இதில் இணைந்திருக்கிற அனைவருக்கும் தமிழ்நாடு அறிவியல் இயக்கத்தின் சார்பிலும் PSL குரூப்பின் சார்பிலும் அனைவருக்கும் மீண்டும் ஒரு முறை தேசிய அறிவியல் தின வாழ்த்துக்களை அன்போடு தெரிவித்துக் கொள்கிறோம். அன்பு நண்பர்களே, தேசிய அறிவியல் தினம் ஒவ்வொரு ஆண்டும் பிப்ரவரி 28ஆம் நாளை தேசிய அறிவியல் நாளாக கடைபிடித்து வருகிறோம். நம்முடைய வாழ்க்கையில் அறிவியலும் அறிவியலாளர்களும் அறிவியல் முன்னேற்றங்களும் வழங்கி ஒரு முக்கியத்துவமிக்க பங்களிப்பை நினைவு கூர்ந்து கொண்டாடுவதற்காக இந்த நாளை நாம் அனுசரிக்கிறோம். அறிவியல் என்பது சுருக்கமாக நாம் விவரிக்க முற்பட்டால் அது ஏதேனும் ஒரு உண்மையை பற்றிய புலனாய்வுக்காக பரிசோதனை ரீதியாக அடிப்படையில் அமைந்த முறைப்படுத்தப்பட்ட அறிவு என்று சொல்லலாம். இந்த சொல் லத்தீன் மொழியிலிருந்து பெறப்பட்டது. இதை உலக புகழ்பெற்ற அறிவியலாளர் ஒரு முறை சொன்னார், அறிவியல் என்பது கெட்டி தட்டி போன வரட்டு தத்துவங்களை கொண்ட மதம் அல்ல. அறிவியல் என்பது கெட்டி தட்டி போன வரட்டு தத்துவங்களை கொண்ட மதம் அல்ல. மாறாக தவறுகளை திரித்து கொண்டும் புத்தாக்கங்களை முன்வைத்து கொண்டும் செல்லும் முன்னேற்றமாகும். அறிவியல் என்பது தவறுகளை திரித்து கொண்டும் புத்தாக்கங்களை முன்வைத்து கொண்டும் செல்லும் முன்னேற்றமாகும் என்று கூறினார். அந்த கூற்று மிக சரியானது. இந்த ஒட்டுமொத்த உலகமே நம்முடைய இந்த அறிவியல் கூற்றுக்கு சிறப்பான முறையிலே ஒரு கட்டமைப்பை ஏற்படுத்தி இன்று அறிவியல் தொழில்நுட்பத்தை பெரும்பாலும் வழிவகுத்திருக்கிறது. அதற்கு மனமார்ந்த இன்றைய நாளில் நாம் அனைவருக்கும் நன்றி செலுத்த வேண்டியிருக்கிறது. அதே போல அறிவியலை சரியான முறையில் பயன்படுத்த வேண்டியிருக்கிறது. இன்றைய சூழலில் நாம் அறிந்திருப்பது போல அறிவியலும் பயன்பாட்டு அறிவியலும் படிப்படியாக மேம்பட்டு வருகிறது. அது நமது வாழ்க்கையை மிக எளிமையாகவும் மேம்படுத்தும் விதத்திலும் கடத்தி செல்ல உதவுகிறது. பிரச்சனைகளை அறிவியல் கண்ணோட்டத்துடனும் அறிவியல் மனப்பான்மையுடனும் அணுகி தீர்வு காண்பதற்கு ஒரு திசை வழியை காட்டுகிறது. எனவே நாம் அறிவியலை தவிர்க்கவே முடியாது. அறிவியல் நமக்கு இவ்வளவு காலமும் வழங்கி இருப்பவை அனைத்தையும் பற்றிய எல்லா நினைவுகளையும் மீண்டும் நினைவு கூட்டி கொள்வதற்கு பயன்படும் மிக முக்கியமான வாய்ந்த நாள் இந்த நாள். இந்த நாளில் நாம் ஒரு சிறப்பான முறையில ஒரு கருத்தரங்கு ஏற்பாடு செய்து கலந்து கொள்வதில் பெருமை அடைகிறோம். இந்த தேசிய அறிவியல் தின வரலாறு மற்றும் நான் குறிப்பிடலாம் என்று நினைக்கிறேன். இந்த நாளில் வரலாற்று முக்கியத்துவத்தை பற்றி நாம் அறிந்து கொள்வோம். பிப்ரவரி 28ஆம் நாள் ஏன் அறிவியல் நாளாக அனுசரிக்கப்படுகிறது, எப்போது முதன்முதலாக கொண்டாடப்பட்டது, இதற்கு நிறைய விஷயங்கள் நம்ம சொல்லியிருக்கோம். சர் சி வி ராமன் என பிரபலமாக அறியப்பட்டுள்ள சர் சந்திரசேகர் வெங்கட்ராமன் இந்தியாவின் ஆக புகழ்பெற்ற தன்னிகரற்ற அறிவியலாளர். ராமன் விளைவு என்று அறியப்படும் தனது ஆய்வு கோட்பாட்டை பரிசோதனை மூலம் நிறுவி அதை உலகுக்கு அதிகாரப்பூர்வமாக அறிவித்த நாள் 1928ஆம் ஆண்டு 1928 பிப்ரவரி 28 ஆகும். அவர் நிகழ்த்தியது ஒரு மாபெரும் கண்டுபிடிப்பாகும். இந்த கண்டுபிடிப்புக்காக அவர் உலகம் முழுவதிலும் அறியப்பட்டவராக ஆனார். ராமன் விளைவு என்ற கண்டுபிடிப்பு காரணமாக அவர் கௌரவிக்கப்பட்டார், விருதுகள் வழங்கப்பட்டது. 1930 பிசிக்ஸ்க்காக அவருக்கு நோபல் பரிசு வழங்கப்பட்டது. இந்தியாவின் மிக உயரிய விருதான பாரத ரத்னா விருது இவருக்கு 1954 வழங்கப்பட்டது. அதே போல உலக அளவில் மதிக்கப்படும் மாபெரும் லெனின் சமாதான பரிசு இவருக்கு 1956 வழங்கப்பட்டது. இது போல ஒரு வரலாற்று சிறப்பு மிக்க ஒரு செயல்பாட்டாளர் நம்முடைய இந்தியாவில் தமிழகத்தில் பிறந்து அறிவியல் சார்ந்த பல விஷயங்களை நமக்கு வழங்கி இருக்கிறார்கள். எனவே நண்பர்களே, இதை நாம் முன்னெடுத்து சொல்ல வேண்டும். அதே போல இந்த நாளில் கொண்டாடப்படுவதின் குறிக்கோளும் நோக்கமும் நாம் அனைவரும் அறிந்து கொள்ள வேண்டும். அது ரொம்ப முக்கியமான ஒரு விஷயமாக நாம் கருதுகிறோம். அந்த அடிப்படையில் தேசிய அறிவியல் நாளில் முதன்மையான நோக்கம் நாட்டு மக்கள் அனைவருக்கும் அறிவியலை பற்றிய விழிப்புணர்வு ஊட்டுவதே ஆகும். நாம் எப்படி இந்த PSL போன்று பல விஷயங்களை நாம் விழிப்புணர்வு மூலமாக கருத்து ரீதியாக ஒரு ஆய்வு ரீதியாக தெரிவிக்கிறோமோ அது போல ஒரு மக்களுக்கு ஒரு விழிப்புணர்வை ஊட்டுவதே இந்த நாளின் நோக்கமாக இருக்க வேண்டும். அதோடு கூடுதலாக குழந்தைகள், மாணவர்கள், கல்லூரி மாணவர்கள், ஆசிரியர்கள் அவர்களுக்கெல்லாம் எதிர்கால பணிகளுக்கான பாடமாக அறிவியலை தேர்வு செய்வதற்கு உத்வேகம் ஊட்டமாக இருக்க வேண்டும். எல்லோரும் அறிவியல் அறிவை பெற வேண்டும். அதே போல அறிவியல் பாடங்களை ஆய்வுகளை செய்ய நாம் ஒரு வழிகாட்டுதலை செய்ய வேண்டும். நமது நாட்டை முற்போக்கான திசையில் இட்டு செல்ல போகும் எதிர்கால சந்ததியினர் அவர்கள்தான் என்பதால் அவர்கள் நாம் புறக்கணிக்க முடியாது. அறிவியலின் பால் தாகத்தை கொண்டவர்களாக இருக்கும் மாணவர்களை கவர்ந்து ஈர்க்கும் உத்வேகமூட்டவும் அறிவியல் தொடர்புடைய பல நிகழ்வுகள் ஏற்பாடு செய்யப்பட்டு நடத்தப்படுகின்றன. அதே போல நண்பர்களே, இந்த தினத்தில் நாம் இந்தியாவிற்கான மக்களுக்கான அறிவியலை கொண்டு செல்ல நாம் அனைவரும் நிறைய விஷயங்களை செய்வோம். உண்மையிலேயே இந்த வருடம் தேசிய அறிவியல் தினத்தோட ஒரு தீமாக ஃபியூச்சர் ஆஃப் எஸ்டி, அதாவது சயின்ஸ் டெக்னாலஜி அண்ட் இனோவேஷன் இம்பேக்ட் ஆஃப் எஜுகேஷன் ஸ்கில்ஸ் அண்ட் ஒர்க் என்ற தலைப்பிலே நமக்கு இந்த வருடத்துக்கான ஒரு தீமை வழங்கியிருக்கிறார்கள். அந்த தீமோட நாம் இந்த அறிவியல் அறிவை அனைவருக்குமானதாக கொண்டு செல்வோம். இது போன்ற PSL போன்ற பல இயக்கங்களை நாம் கொண்டு செல்ல வேண்டியிருக்கிறது. உங்கள் அனைவருக்கும் மீண்டும் ஒரு முறை அறிவியல் தின வாழ்த்துக்களை தெரிவித்துக் கொண்டு வாய்ப்புக்கு நன்றி கூறி விடைபெறுகிறேன். நன்றி, வணக்கம்.
TRG, can you introduce the speaker?
Okay. Welcome to all of you. Today is a great day because National Science Day. As Sethuraman mentioned, on 1928, February 28, Raman discovered, along with his student Krishnan, Raman effect, which is called Raman effect. And it is an extraordinary work. And very interestingly, some few years back, before that, it was expected by a German scientist, Merkel. And around the same time, it was also done by a couple of Russian scientists, but Raman beat them all and got the results which he could publish. And he was so confident that he will get the Nobel Prize in February when he did the work in 1928, February. And as you know, Nobel Prizes are announced in October and it is given in December. In those days, there are no flights, so people have to go by ship. And Raman used to book a ticket to Stockholm by ship by August itself, so that he was sure that he will get it. Unfortunately, he didn't get it in 1928, he didn't get it in 1929, and his expectation proved to be right, and as usual, and he got it in 1930. Raman 1930 வருடம் நோபல் பரிசு பெற்று இந்தியாவிற்கு பெருமை சேர்த்த நாளாகும் Raman effect, and we are very happy. Raman, this day is celebrated because the scientific temper is part of our constitution, and part of our science forum activities also. We want to spread the message of scientific temper, and this is the reason we are holding this meeting on this day. Now, the most important thing is we are going to talk about Himalayan glaciers, and there are two speakers. One is Shankar and second is Jayangonda Perumal. And first I will introduce Shankar because he is going to be the first speaker. And Shankar, I should tell you, he was known to me for the past 40 years. When I was a research student finishing stages, he started his career as a research student in Tata Institute of Fundamental Research. And then, of course, both of us were interested in similar areas, high energy physics at that time. And he came to Math Science, Institute of Mathematical Sciences, when I was in Loyola College at that time. And then moved to Kanpur IIT also. And he joined along with me in Institute of Mathematical Sciences in 1991. We even collaborated in a few of the papers which are on quantum field theory. And I'm very happy to have been associated with him all this while. And he has varied interests. He is a versatile person. He has a lot of interest in hiking. He was interested in biking and great activist. And he has been always helpful to Tamil Nadu Science Forum whenever we hold the meetings. And last maybe about 7 to 8 years, if I'm right, he was interested in climate change issues and the glacier. And that is why he got himself associated with modeling about the glaciers. And he took it very seriously. He used to go at least 2 to 3 times a year to Himalayas. Even when he was a physicist working, and he was doing modeling activity with people associated with Srinagar, if I'm right, and a lot of activity about measuring the Himalayan glaciers and changes in that, and getting the correct model. And this is his thing. And I'm very happy when I asked him to speak about this, because recently this disaster took place, and we were discussing, Vijayan and myself. Then we decided we should have a couple of people, one who will explain the facts and about the glaciers itself, followed by the reasons for the disaster which took place in Chamoli. Incidentally, I have also gone to some of those places, very interesting places, but that's beyond the point. Now, Shankar will speak about the Himalayan glaciers and facts about the Himalayan glaciers, how they grow and how they affect our climate, etc., which is an expert on that. And then after him, we will get Jayangonda Perumal to talk about the actual event which took place at Chamoli, and we will hear him also. Following that, we will have question and answer sessions where people can raise questions. And before that, if you have any question, you send it by chat in this thing. And also you can, after the meeting, if you want to directly ask a question, you can raise your hand, and our coordinators will allow you unmute your mic, and then you can ask the question after that also. There is no problem. Anyone can ask the question. And it is when somebody said that don't express your opinion, what is meant is express your opinion about the meeting, about our work, just being that, not about the politics and other issues which are involved, extraneous to the meeting. And that is all that is meant. So try to keep the activity and learning process of science of these glaciers, and also the lessons for our public. Now I will invite Shankar to start his lecture. You can share your screen.
Yeah. So good afternoon to all of you. And so is my screen visible?
Yes.
Yes.
So firstly, let me thank Tamil Nadu Science Forum for inviting me to give this talk. Topic is going to be on generally about glaciers, and in the second part I'll come to the Himalaya. So this is the outline. First I'll talk about all the glaciers on Earth is called the cryosphere, which is all the naturally occurring ice on Earth. Then I'll talk a little bit about climate change, and then Himalaya, glaciers of Himalaya. And finally, because this session is sort of motivated by this disaster, some general aspects of hazards in mountains or in Himalaya in particular. So this is the way we are taught in school. We sort of compartmentalize the whole Earth system into different spheres: the atmosphere, the biosphere, which is all living things on Earth; cryosphere, which is all the ice on Earth; hydrosphere, which is all the water on Earth; and the land. Now, we compartmentalize it in our heads because of our limited capability of understanding, but all these things are one integrated whole, actually, and powered by the sun. So each part of this, there's no sharp division. Each part influences the other, and it's really a whole integrated Earth system. So where is the ice on Earth? You can see the picture here that mainly this is near the North Pole. This whole part near the South Pole is Antarctica over here. And then there are some in the mountain ranges, the Himalayas and Andes and so on. So most of the ice on the Earth is in the polar region. So this is the Google Earth photo, which you can see from on top of the North Pole. And this is the Greenland ice sheet. There will also be floating ice, which is not shown in Google Earth over here. The North Pole is underwater. There's no land over there. So it is a part of the ocean. And this is the view from on top of the South Pole in the same scale. you can see this is by far the largest piece of ice on Earth, the Antarctica. And this is land-based ice because Antarctica is land. And compared to that, you can hardly see any white over here on the Himalayas. So this is just to say that almost all the ice on Earth at the moment is in the poles. But when we zoom in, we see that there is a lot of ice, and this is the satellite photo of the Himalaya. And in fact, it is sometimes in glaciology called the third pole, because outside the two poles, this is where the maximum concentration of ice is. Some other ranges where you can see a lot of glaciers. There is the Andes in South America. You can see a whole line of these things here. And these are the Alps in Europe. And there are several other places also. Now, why is the ice here? Ice will be, naturally, it will not melt if the place is cold. So this gives you a temperature distribution of the Earth. The blue is cold and the red is hot and intermediate you can see. So as you expect, the coldest regions are the poles. This is the South Pole and this is the North Pole region. South Pole is a bit colder because there is more land over there. And then as you go towards the equator, it gets hotter and hotter. But you can see at low latitude, there's a bit of blue here, which means there's a cold region. And this is because this is the Tibetan Plateau, which is at about 4,000 meters high, a huge region about elevation of 4,000 meters. So either high latitudes or high altitudes. These are the cold regions. And so you find all the ice in either the poles or high mountains. So how much ice is there right now? You can roughly, totally it's covers about 10% of the land area. As you can see over here, most of it, about more than 8% is in the Antarctic ice sheet, 1.5% in the Greenland ice sheet, and all the mountain glaciers together constitute about 0.5% of the. And this is the thing that if all this ice melted, how much the sea level would rise. This again gives you an idea. But however, sea level is not going to rise by so much in the immediate future. All this amount of ice is going to take a long time to melt, if at all it does. Now, ice, these are not just static. They have dynamics. They change. So this gives you a cartoon of the ice sheet. So this will be the coldest region, and it snows over here, and the snow becomes ice. And then because of its own weight, it flows, and this gives you the flow pattern. And then it goes off into lower latitudes. Over there, either by melting, but mainly by calving. Then once it reaches the lower latitudes, icebergs break away from the edges. And that's how mainly these Greenland and Antarctica ice sheets lose their ice. There is some amount of melting also, but their dominant way they lose ice is by calving. And these icebergs float off into the ocean and eventually melt over there. This gives you a picture of what we call a valley glacier. These are the glaciers in the mountains. They flow down valleys. So they accumulate ice in the higher altitude because here the input of ice into glaciers is precipitation. That is rain, and at high altitudes it snows. So the snow falls in the high altitudes, and after a couple of years it becomes ice. And that flows under its own weight down the valley. When it reaches the low altitudes, it becomes warmer and it starts melting over here. So the dynamics slightly different, but basically you can see that the input of ice is precipitation, that is snow, and the output of ice is either calving or melting. So it is glaciers are strongly affected by climate. The input, if the precipitation changes, the input of ice changes. If the temperature changes, then the output of ice changes. So glaciers and climate are very intimately tied to each other. Now, first, just to give some idea of time scales, we are going to talk about history of the cryosphere and the Earth. So as we understand it now, the universe itself started about 14 billion years ago. Earth has been around for about 1/3 of that time, roughly 4.5 billion years ago. Our species has come in only about 300,000 years ago. So we've been, our whole Homo sapiens, from the point of view of the Earth, is a very instant phenomena. We just have about come. So I'll first talk about long time scales changes, and then come to time scales which are more of human interest, that is, say, 1 century or so. Now, to understand the climate change, first, climate change is driven by global warming, as you know. So there's one basic question: what sets the temperature of the Earth? Average temperature of the Earth is roughly 14 degrees centigrade. Why is it not 100? Why is it not -60? So the person who first asked that question is Joseph Fourier, who was in the first half of the 19th century, a physicist. He was a pioneer in the theory of heat. And so once he started understanding heat, this was a natural question that he asked. Fourier did not, enough physics was not developed for Fourier to understand what sets the temperature of the Earth. But the noteworthy thing about it is that he considered, among various things, the effect of the atmosphere. And he was the first person in 1824 to hypothesize the greenhouse effect, which we know is of crucial importance today. So the answer, by the end of the 19th century, the answer was known. What sets the temperature? Answer is energy balance. So here we have the sun, and it is heating up the Earth, mainly because through visible light. So it emits light, which we see every day, sunlight. The sunlight gets absorbed by the Earth and heats it up. Now, any warm body in its turn emits. As you can see, if you put your hand near a stove or a pan that is hot, even without touching it, you can feel the heat coming out of it. And that is what we call the infrared radiation or heat waves. And so hotter the body, the more heat it emits. So at some point of time, the amount of energy that it is emitting becomes equal to the amount of energy that it is absorbing, and that's where the temperature stabilizes. So that's why we call the temperature set by this energy balance. That the incoming absorption of visible light is equal to the outgoing emission of infrared. Right. So why does climate change? Any change in this parameters of this energy balance will make the climate change. So there are changes in the incoming energy. This is because there are very small changes in the Earth's orbit parameters, which I'll describe in the next slide. And so because of the orbit parameters slightly changing, amount of energy coming in changes very slightly, but over a long period of time, it affects the climate. Then the amount of all the light that falls on the Earth is not absorbed. Part of it is reflected back. How much is reflected back depends on the nature of the land. So if there are a lot of aerosols in the atmosphere, pollution like volcanoes, then some more part of it will get reflected back. If the area of the polar caps is large, more of it will get reflected back. So the change in the nature of the land, reflectivity of the land, is one factor that affects how much energy gets absorbed by the Earth. Then changes in the outgoing energy, there are several, but this is the main thing, that the greenhouse effect, which was initially hypothesized by Fourier, which traps some of the infrared which is emitted by the Earth. It gets trapped by the atmosphere and doesn't escape off to space. So the higher the trapping, then less the energy that goes out, and that causes heating. So that's one of the factors. So this is what I was talking about, change in the orbit parameters. They periodically change very slightly. The Earth's orbit is an ellipse around the sun. This ellipticity changes slightly once with a period of about 100,000 years. then there is this angle that the Earth's axis makes with the planetary plane, around 23 degrees right now. That changes from 22 to 24 periodically with a period of 40,000 years. And then that axis also rotates in what we call nutation occurs with a period of 20,000. So now it is more or less believed that long-term changes, slow changes in the climate were mainly due to these periodic changes in the Earth's orbit, which are called Milankovitch cycles after the astrophysicist Milankovitch who discovered that. And then there's the thing that stops the output energy. So this was, I shouldn't say discovered here, hypothesized is the correct word. And then slowly it was established by work later. So whatever heat is emitted, there are the greenhouse gases, carbon dioxide, water vapor, methane. These are some of the main gases. They absorb the infrared and re-emit it back to the Earth. So what would have escaped into space, part of it gets trapped. And that causes the heating. And all this was sort of understood by the end of 19th century. So then how did the climate change in these periodic variations in the orbit parameter, Milankovitch Cycles? So this gives you a record of the temperature of the Earth measured by some indirect way, which I won't go into. In fact, they are measured using the ice from the Antarctic ice cores. But so this is the present time. The red shows the temperature. So 0 is with respect to current temperature, and cold periods are where the average temperature would have been about 10 degrees lower than what it is today, and the high periods are where it would have been higher. So you can see it as you go back in time, it was very cold. This was what we call an ice age, then warmed up again, then cold again, warmed up again, cold again. So these cycles are called the glacial cycles, or what commonly we call ice ages. Ice ages would have been these low temperature parts. And also you can see over here recorded the carbon dioxide level. That also varies very periodically, up and down, up and down. And so far in the past, the carbon dioxide concentration in the atmosphere was lagging behind the temperature. So the cause was the temperature and the carbon dioxide variation was the effect. Recent times, as we will see more, there's been a sudden increase of carbon dioxide into the atmosphere, and now that is driving the temperature. So this gives you a conception of how much the last ice age, which was about 24,000 years ago. And so this is also called the last glacial maximum. This is a view from above the North Pole. This is the amount of ice today, that is Greenland. And you can see large portions of the northern hemisphere were covered by ice during this last ice age. So that last ice age would have corresponded to this cold period, which was about 25,000 years ago. Then there's one interesting thing, that there's the temperature affects the amount of ice. The amount of ice also in turn affects the temperature, in the sense that once the ice cover increases, then the amount of light that gets reflected back from the sun also increases. So then less energy is absorbed by the Earth, which makes it go colder. And this is a runaway effect. And there's a striking possibility of what is called a snowball Earth, that there may have been times, and there is evidence of this, that there may have been times where the entire Earth was covered with ice. I don't know much about this. There's what type of geological evidence is there, but I just presented it since I find it very fascinating. Earth is, of course, not covered with ice, but there is one of the moons of Jupiter called Europa that is believed to be completely covered with ice. So this is a photo of Europa taken. It's got the smoothest surface of any planetary body that we know. And planetary scientists believe that it is a snowbound moon, in the sense it's completely covered with ice. Now, in the ice ages, when large amount of the water on Earth is in the form of ice, the sea level goes down. So the total amount of water on Earth is more or less conserved, roughly the same. So during the ice ages, most of it is on the land in the form of ice. Then when the ice melts, it flows into the ocean and the sea level rises. So forget the details in this graph. This gives you an estimate of the sea level by various indirect means in the past. So this is the current time. And as we go, this is 2,000 years ago, 4,000 years ago, 5,000 years ago, and so on. So you can see in the last glacial maximum, about 20,000 years ago, the sea level was more than 100 meters less than what it is today. Then as ice started melting, it slowly went up. And for the past 5,000 years or so, we've had a very steady climate and consequently a very steady sea level. So the sea level and the cryosphere, they are clearly very related. One goes up, one increases, the other decreases, then the other increases, the other decreases, so on. This interplay is constantly going on and has been going on for the past at least 800,000 years, for which there are pretty good evidence. So here's a summary of ice and climate at very geological timescales. That there are cycles, the climate has periodic variation, and in the cold periods there is more ice on the land, we call them the ice ages. Then the warm periods, the ice melts, there is less ice and the sea level rises. Now let us come to some more recent time and look at the temperature history for the past, say, 10,000 years or so. So this gives you the roughly past 10,000 years temperature history. This is the current time, and this is 10,000 years ago. So this 0 is with respect to current temperature. So it was quite steady. It was about slightly colder earlier, then warmed up a bit, then went down a bit. This period is called the Little Ice Age. But you can see past 5,000 years or so, it's been a very steady climate. And then past 100 years, a sudden rise. So this is shown over here. So this is really the cause of, that the past 200 years or 150 years climate temperature. And this graph is based on actual instrument data, because past 100 years or so, there have been weather stations all over the world and they've been collecting data. So I put this in a tabular form over here. So you can see that in the past, more than for the past, meaning when you're talking about 1,000 years ago, the warming rate was very slow. There was even the most fastest periods of warming in the past, which is some 0.1 degrees per century, is about 10 times lower than what it is today. So this is the reason for worry right now, that the Earth is warming around 10 times faster than it ever warmed before in the past 800,000 years. And typically about 50, 100 times faster than typical rates in the past. This warming causes a lot of climate change, meaning if it is warm, there'll be more evaporation from the oceans, the wind patterns change, and this is causing very rapid climate change today. And that is why all the current worry. And now I think it's also well established that the primary greenhouse gas is the carbon dioxide emissions. That though there are water vapor is actually the largest amount of gas present, the amount of water vapor in the atmosphere is also controlled by how much carbon dioxide is emitted. And there is a lot of evidence of that now. And so this shows the carbon dioxide levels. This is about 10,000 years ago, and this is today. It was slowly going up, and then this is roughly Industrial Revolution. Suddenly, a huge pulse of CO2 has been pumped into the atmosphere. And that pulse is what presumably caused this increase in the temperature. And this is showing the carbon dioxide. This is laboratory measurements. The carbon dioxide parts per million in the atmosphere in the recent half century or so. This is called the Keeling curve after Keeling, who first made these measurements in the 1960s. His lab has continued this. And you can see that the concentration is steadily increasing. Despite all the efforts, so the IPCC was set up in 88. After that, there have been various conferences. These are some of them: Kyoto, Copenhagen, recently in Paris, where governments try to meet and try to find ways to limit CO2. But on the field, it has had no effect. You can see that this curve is just constantly rising. If the temperature has to be controlled, this curve has to flatten. And as of now, there are no signs of that happening. So to summarize, in past geological times, the climate change was driven by the Milankovitch cycles, mainly by the changes in Earth's orbit. Last few centuries, it has been driven by greenhouse gas emissions, primarily carbon dioxide. And as of now, the amount of CO2 being pushed in is steadily increasing per year. I mean, the level of CO2 in the atmosphere has been steadily increasing, not showing any sign of leveling off. So now let me just say, let me come to the Himalaya. So I've been involved, what I'm going to talk is basically based on experience coming from collaboration with Hemati Nandan Bhagunath, Garhwal University, Professor Nanwal over there in the Geology department, and these are his students. Orgho Banerjee was a faculty in IISER Pune, and Saurabh is a student. And these two are project assistants who are from a nearby village near the glacier that we go to. And they know the region like the back of their hand, and their experience is crucial. Without them, we couldn't have done any work over there. So this is the study area. This is showing, this is all Uttarakhand, and this is showing the main tributaries of the Ganga. So this is the Gangotri Glacier, and the Bhagirathi River comes out of that. This is a glacier called the Chorabari Glacier, and this is Kedarnath, and the Mandakini River comes out of that. And this is the twin glaciers, Satopant and Bhagirath Khadak, and this is close to Badrinath. And this yellow spot is the Mana village, where our project assistants are from. And this area is, so this is the Alaknanda River. It comes down like this and joins with Mandakini here. And finally, the Alaknanda and the Bhagirathi join. After that, the river is called Ganga. So by the way, the Dhauli Ganga would be coming something like this, the place where the recent flood took place. And the recent flood would have been somewhere in this region. So this is all Chamoli district. And so this region is called the Upper Alaknanda Basin. And that's where we concentrate our study. Now, why are glaciology studies interesting? One of reason quoted is that many of the rivers originate from the Himalaya. So 3 of the major river basins in South Asia originate from the Himalaya. This is the Indus Basin, which gives water to this part, mainly Punjab and Pakistan. This is the higher altitude part, so it's called the Upper Indus Basin. And this is the Lower Indus Basin. Then there's the Gangetic Basin. The Ganga flows through this part, and this is the Upper Ganges Basin. And this is the Gangetic Plains. And this is the Brahmaputra Basin. The Brahmaputra flows like this. It also starts somewhere like this, flows like this, comes down here into Bangladesh, and eventually joins the Ganga over here. So now, how do glaciers affect the river flow? Very often we think, it's stated that the glaciers are the source of the water to these rivers. That is, of course, not true. As we are taught in school, there's a water cycle. There is no source or sink of water. It's a complicated process, but basically it evaporates from the oceans, comes over to the land where it falls in the form of rain, snow, hail, etc. Some of it falls as ice, and that is or snow, and that is becomes a glacier. And then it melts back again and goes back into the ocean. So this water is constantly cycling over here. Glaciers are a part of this water cycle. So what role do they play in the water cycle? As I said, they are not the source of water. The source of water in land is always the precipitation. In the higher altitude, it is snow. In the lower altitude, it is the rain. So glaciers should be thought of as reservoirs of water. That these reservoirs fill up when during the time it snows, typically winter, summer also in the Himalaya, and it empties typically high in the summer. So it forms a buffer of fresh water, and if they disappear, what will happen is that the seasonality of flow will be affected. And so as I said, the total discharge of the river is average over the year. In the long term, is not likely to be affected. That will be affected in India if the monsoon gets affected by climate change. Indian summer monsoon is one of the main sources for most of our rivers. So this is some, to give you how much glaciers contribute to the flow in the river. This is some initial work, modeling work done on Himalaya scale. This is as I said, initial word, not the final word. A lot more research needs to be done to see how reliable these numbers are. But you can roughly see this in the Indus Basin, about 60% of the upper Indus. So by upper Indus, we mean river at the elevations of about 2,000 meters, which will be typically the altitude of Simla, Darjeeling, that type of hill stations that we talked about. So it's about 60% of the water in the upper basin is coming from glaciers and snow. In the Ganges, Indus is very dry, so larger fraction is coming from glacier and snow melt. In the Ganges, about 20% is from this thing. Because again, Ganges basin, the summer monsoon is very active and it is quite wet. And this is again about 20-25% from the Brahmaputra basin. This gives the same picture, the different types of contributions to the river flow, and the glacier melt contribution is blue. And this is again the contribution in the upper basins. What about contribution to the total flow over the entire river? This is a rough calculation that I've done. So these are roughly the total discharge of the rivers in a year. And so it's about 1,400 kilometer cube per year of water that flows through it. Then 40,000 square kilometers is the measured area of the ice all over the Himalayas. This is a well-measured number because you can measure it using satellite images. And about 1 meter per year, say, melts on the average. So when you do this calculation, you find that the total contribution to the river flow is just a few percent. And just to, for you to get a feel for that, this gives you the Google Earth picture of the river basins. Now it is raining all over here. The entire Gangetic plain, everything is raining. And as I said, rain or precipitation is a basic source of water. A small fraction of part of the precipitation is ice covered. So, roughly speaking, whatever falls in this region will become ice and then contribute to glacier flow. But the huge region here it's also raining. Rain is falling here and flowing into the Ganga. The catchment of these rivers are huge. So And even in the mountain regions, large amount of the rain gets trapped and goes into the ground, comes out as springs, etc., etc. So they are significant. Glacier melt is significant to rivers in the upper basins, not so much in the entire basin. And even in the upper basins, they are about 20%. But as people point out, during drought years, I mean, like for example, here, 11 and 20% total is during a normal year. But suppose there's a drought year where monsoon fails, then the glacier contribution will come anyway, and it will become more significant than. So now the one question is, because since the climate is changing and it is warming, when will the ice, if the warming continues forever, clearly all the ice will melt. How long will it take? Answer is not known yet. There are just some guesses. And so I'll just give you some results which give you some idea of how fast the ice is vanishing. So this is some work based on modeling, because volume of the ice cannot be measured directly. From satellite photos, we only measure the area. But then you have to use some models, and they basically predict that Himalaya will lose about 30 to 60% of the ice by the end of the century, with respect to the beginning of the century. Now, is it 30% or is it 60%? Depends on how the climate change occurs on this thing. But this is so these are the numbers based on two typical climate scenarios. But the area changes are much lesser. And this is some recent work that we have done based on satellite data in the upper Alaknanda basin. All said and done, we have, for the past, what we find is that for the past 50 years, the area loss has been roughly 0.1% to 0.2% per year, which is pretty small rate, which means that if this trend continues, the glaciarized area will reduce to about 30% in the next 700 years or so. Much slower than the volume decrease of the estimate of the whole ice. But basically what that means is that the ice loss is going to be by thinning of the glaciers. So as the melt occurs, not the area and the length loss is not so much. The main loss will be the glaciers will, the area remains roughly same, but they become thinner and thinner, and that's how the loss is going to be. But as I said, there are much uncertainties in all these calculations and modeling. Every basin is different. Each of them have to be measured independently. Modeling has to be done, and that's a lot of work left for the future. But overall, if current trends continue, all the ice will vanish in the time scale of centuries, not in the time scale of thousands of years, not in the time scales of tens of years, but in the time scale of centuries. So finally, something about there are natural hazards in the Himalaya. There are plenty of types of natural hazards. Now, plot shows you earthquake is one big one of them. So this plot shows you all the earthquakes that have occurred with magnitude 5 or above from 1800 to 2000 in. So you can see they are concentrated along this region. And these are the Himalayas. So the Himalayas lie on a fault, and it's earthquake-prone area. So this is one major natural hazard, and there's not been a big earthquake for some time now, but it's a question of time before there is. And this is completely unpredictable. As of now, earthquakes, there's no way of predicting earthquakes. So when it's going to come, where it's going to come over here, etc., we don't know. But overall, it's clear that this is a fault line, and there are bound to be earthquakes sooner or later. And it's a fault line. The reason also, is basically The Himalayas themselves have come because of the fault line. This shows the history of the continents, some picture. So here one piece broke away from Africa long time ago, went to Eurasia, collided with Eurasia here, and that's how the Himalayas themselves formed. So the Himalayas formed at the point where the Indian subcontinent collided with the Eurasian continent, and that's why the uprising. So it is a big earthquake-prone area. Over the time scale of centuries, there are going to be many earthquakes there, and that is one major danger. So questions like what will happen to Tiri Dam if there's a big earthquake near it, unanswered right now. Landslides also keep happening in the Himalaya. Anybody who's gone on road there regularly has got held up once or twice. There'll be a landslide on the road, and few hours there'll be JCBs coming and clearing it up. So landslides are extremely common. But one interesting thing is that typically the villages are built in places where they are not that they are not affected at all, but they are not affected very much. Most of the, whereas on the roads, large number of landslides occur, and they happen all the time. Avalanches is another thing because there is ice and snow on steep slopes. So sooner or later, very often they fracture. So this is a huge avalanche which our team photographed. This is actually the accumulation zone of the glacier we study called the Satopan Glacier. And this is all the ice flowing down. And this is a huge avalanche that occurred on this mountain face on 30th September 2014. In fact, some of our team made a movie of this. They're extremely common. So when we go to the field, you keep hearing them. And very often you see them. There are lots of photographs, etc. Now, we don't have any problem with avalanches simply because we don't go into avalanche-prone areas. I mean, we are scientists and not adventurers, so we don't take data at the risk of life and limb. There are local people who advise us where it is safe, where it is not safe. And it's quite easy to make out which areas are avalanche-prone, and we don't go there. Local people also don't go into these areas, and so avalanches basically affect people who go there. So mountaineers and trekkers who go there for adventure. Unfortunately, they are accompanied by mountain guides and porters who go there for livelihood. And these are the people who die during avalanches. And the other set are soldiers based in high altitudes. According to me, there's no reason for them to be there, but they are there due to our human concept of politics and so on. So they are also forced to be there as a part of their jobs. And many of them, we keep losing at Siachen Glacier, for example, due to the harsh conditions there. Finally, the flash floods, which we'll hear more about in the next talk, they can have a variety of causes. One is called glacial lake outburst floods. So lakes form near glaciers, which are dammed by glacier deposits called moraines. And these moraines are not very stable, and sometimes they collapse, leading to a breach. Then all that water in the lake flows into the stream and causes a flood. So this was partially due to the reason for the havoc in the flood in Mandakini that devastated Kedarnath. But this is not the only reason for these flash floods. Like I'll show you in a minute, the floods that occurred in other parts of Alaknanda, other parts of Uttarakhand in 2013 were not due to glacier outbursts. There was basic cause was heavy rain. And this time's flood is also probably not because of any glacial outburst, but we'll hear more about that in the next talk. So this is just to give you some idea of nature of these flash floods in the mountains, that they carry along with them a thick amount of debris. So this is what we mapped the origin of the flood in Alaknanda in 2013. So these are the places where the flood originated. This is a stream called the Khirongar that joins with the Alaknanda River, and this entire region was thickly covered with debris. Now here also, though it started from glaciated regions, there were no lakes or no signs of lake outbursts or anything over here. Our conclusion was that this was simply caused by very heavy rain. So this is a dam downstream of that area called the JP Dam. And you can see, similar to what happened here, that dam was completely silted up. And this is all the debris that gets transported along with these floods. Debris means boulders, rocks, stones, mud, clay, etc. They all come down when the water flows down the river. And this was completely silted up. It took about a year or two for them to clear it. This gives you some idea of how this debris causes devastation. This is a temple that was built. Temple that was built on the banks of the river near the dam that I showed you in the slide. This is before the flood and this is after the flood. This is to show the size of the boulders that are carried. You can see that this structure has been destroyed because along with the water, these huge boulders were rolling around. And that is the thing that makes these mountain floods, the destructive power of the mountain floods is not just the water alone, but all these boulders, etc. that also. So let me finish by saying that the events, these floods, earthquakes, landslides, avalanches, these are all natural events. But disasters are typically human-made. I mean, if humans are not there in the risky regions, the event would not have led to such extremes. For example, in this recent event, more than 100 people are missing. Almost all of them are project workers in that dam in Tapova. And you can see there are reports, if you read carefully, that about 40 bodies have been recovered, 30 body parts. Why body parts? Because this kind of flood breaks it up into this thing, all these boulders working down. So that's just my opinion, that I think science should be used to understand nature and adjust to it rather than try to control it. And I mean, I think clearly that what these disasters show us is that the risk assessment have failed in these things. And that's why the huge loss of human lives. So I think I'll stop there and thank you for your attention.
Thank you very much, Shankar. It was very interesting talk, and please wait for the questions after the second session is also over, because the people can pose the questions to both of you.
So I'll stop sharing.
Yes. So now, so this is the very interesting presentation of what is Himalayas. And it is personal experience plus personal work of Shankar, along with several people he is associated with in those regions. It's very interesting. And I'm sure a lot of people have already, I can see some chat questions which have come up. Probably Vijayan can note it down. And now I'm going to ask Dr. Jayangonda Gopal to present his talk. But before that, let me introduce Dr. Jayangonda Gopal. He is, as mentioned here, Associate Professor at Central University, Thiruvarur. But he's been there for the past about a decade, I think. And he was also main person, project head or scientist associated with the Wadia Institute of Himalayan Hydrology. And he has several records. In fact, a lot of data is available. In fact, I consider him as a new friend. Earlier, I introduced Shankar as my 40-year-old friend. Now I have a new friend, and I'm looking forward to his talk. But the basic thing is he has a lot of expertise about the earthquake, which was mentioned by Shankar earlier. And as we know, Himalayas is earthquake prone, and it is important to study the earthquake proneness in clear details so that we can at least have a risk assessment as mentioned by Shankar, to have a clear understanding of if there is some development, where it should be developed, how it should be developed, what should be the thing, and several questions of that nature. But for today, he is going to talk to us about the actual disaster which took place in Chamoli. And now I request Jayangonda Perumal to provide his perspective about the disaster. Please.
Yeah, thank you, Professor Govindrachan, and thanks to Professor Shankar. Actually, in fact, my name has been spelled wrongly all over the India. In fact, nevertheless, I have been called as a Perumal overall, especially in geology community. I'm not a glaciologist, but I'm a field geologist. I've been working almost 27 years on Himalayas, especially on earthquake-generated landforms. And also I worked a little bit on a brief period in Mont Blanc in Alpine Glacier. And also I've done some work during Kedarnath tragedy. And also I worked in several landslide area wherever it has happened. And I had gone for the investigation and subsequent rehabilitation sites for the people to relocate themselves. So that's what my brief experience so far I have learned from the field from various people as well as from the various surface processes. And today is Happy National Science Day for all of you. And I thank Mr. I forgot his name. I'm sorry, because these people are very recent friend of mine. So Vijay, what is his name, sir? I forgot. Vijayan. Yeah, I really thank to Vijayan, and all this connection came from the Arivial Palagai called Sri Kumar. Like that, I have been in Dehradun. So since then, I have been keep talking with the people. Yeah, actually, I can just switch both languages wherever if I cannot able to explain properly to the audience. So basically, all that today talk is, in fact, it has been repeated, I think, at least twice, but some amount of new slide has been incorporated. And also, I would like to submit my sincere thanks to Professor Shankar. I think he made my talk very simple, but nevertheless, I would like to give in local languages what he has done, actually, how the glacier, all this kind of things he has spoken, actually. So let's see that what happened in Chamoli disaster. Basically, still the ground truthing is yet to be done. That will be done sometime after the April only, because still it's the winter season. So what we have that first-hand information based on the satellite data and also the aerial survey done by our department, Wadia Institute, plus my own experience and other things. I'm going to give some kind of a brief general awareness about that disaster, actually. So I'm occupying both places, but my parent department is where I learned most of the stuff from Wadia Institute. Thank you very much. So the next one is basically meant that the media, they just keep on speculating. In fact, if any kind of an accident happens or any kind of calamity happens, the first person to give the detailed information to the people, actually, basically, they are the medias. So they just keep on saying that the landslide, glacial collapse, or avalanche and GLOF, so many things are there. These are all the fundamentally, there are some new terminology is widely accepted or widely used in the media community. In fact, in Himalaya, the natural hazards, basically, we are talking two things together, actually. In Himalaya is basically a young active mountain, actually. It has the mountain building processes, and also it has a routine natural processes. So when any kind of a human intervention or a societal infrastructure has been developed, like Professor Shankar showed some slides where the building has been developed or infrastructure has been developed on the riverbed actually. So that makes that basically it damages. In fact, the river never damages on its course basically, provided if you start building such kind of infrastructures. So that's number one important take home point. And more or less in Himalaya, construction, destruction, and reconstruction, it's a kind of a ritual. Either you take it in the form of a surface processes, or you take it in the form of an endogenous or a tectonic like earthquake processes, or a flash flood, or any kind of natural hazards. So basically, this is the natural hazards is basically happening because of the intersection of the two processes. It's called the deep-seated, the processes which is operating, which you may not able to see, that is called endogenous, and exogenous is the climate. So tectonic and climate interaction, if they marry and they get this kind of natural resources. So now we will see that what is happened, glacier collapse or a gulf, and we will also talk about the Kedarnath tragedy actually, and little bit on the landslides. In fact, the previous speaker already little bit, but I will just give you some classical example on that. And whatever the material is basically based on the different published sources. And like you see the Google image, when you drive from Delhi, then you hit the somewhere in Saharanpur, then you just see there is all of a sudden, like you can find out like LIC type of building is coming. That's very height kind of elevational differences changes. So that's the important, that all of a sudden you will see the beautiful mountain actually. So there is a mountain, plain mountain and plain area meets. Basically, if you live in southeast coast, you can see the beautiful sea, then seashore meets with the land. But when you go on the mountain land actually, especially Uttarakhand and Himachal Pradesh and Jammu Kashmir, and you go to the Arunachal Pradesh, Assam and West Bengal and Sikkim, you can see that beautiful land is meeting with the mountain. So that's a beautiful elevational differences. So that's about say 500 meters. Then if you see on the inner land of that particular mountain orogeny, you can see that a beautiful snow peak mountains, basically that you can set around 3.5 kilometer elevation. Basically that's about 3,500 meter elevations. There you can see the permanent ice capped mountains. Now if you see, look at the disaster where it has happened in Uttarakhand. So the geology is basically, you can see that if you see on the sub-Himalaya where close to Haridwar and Rishikesh is located, where you will see the beautiful sandstone like a sedimentary rock actually. Then slowly you can see that various grade of metamorphic rocks we can see. The rocks which is on the metamorphic grade, especially on the inner part of the Srinagar Valley, another thing, they had come from the deep source, basically around say 5 to 6, 7, 8 kilometers. Especially granite also comes around 10-15 kilometers depth actually. If you look at the cross section on this, if you draw a little cross section on the Uttarakhand state, you can find that there is elevational differences, and we have the sub Himalaya, then we have the lesser Himalaya, then higher Himalaya. So this is what basically most of the pilgrims, you can see that Kedarnath, Badrinath, and Gangotri, Yamunotri, these kind of pilgrims are located all along this higher Himalaya. They are permanently snow peaked. This is the red arrow. Basically, you can find out that there is a orographic barrier. Basically, what we say that Malay, that is means that southwest monsoon never intrude in the higher Himalayas. So the logic is that when we have the monsoon basically, and whenever during the never rain goes inside the higher Himalayas, there you will find the snowfall will be there. So here the rainfall takes place. So all we studied in the school days also, the sea surface and the land surfaces changes, then slowly this monsoon picks up and comes all the way and hit the Himalayan region and just reflect back into the winter or a retreating monsoon, like Varakilaku Paruvakatu, something like that. So that is why we just say that this Himalaya is very important feature actually, and also in the I think Dr. Shankar already mentioned it's a third pole actually, and this is the Lhasa terrain, basically Tibetan landmass. It is almost roughly located 5 kilometers from the mean sea level. So when you can see that this is what the basically the Himalayan topography, and you can see that, oh sorry, I don't know, there's some problem in the next slide. Okay, if you see the growth of the Himalaya is really growing. Himalaya வந்து சில நேரத்துல பாத்தீங்கன்னா in மீடியால they say that இமயமலை is வளர்கிறது, வடக்கு வளர்கிறது and தெற்கு தேய்கிறதுன்னு சில poetலாம் சொல்லியிருப்பாங்க. So similarly we see that Himalaya is growing at a rate of 6 millimeter per year vertically. So that's the mechanism. So we come across the earthquakes, and all we know that the basically the Indian plate actually, because of the sea is spreading at a rate of say 30 to 34 millimeters along the southeast ridges on the Indian Oceans, that becomes rifting part, and slowly that because of that this Indian plate is moving at a rate of 30 to 40 millimeters. Because of that basically this Himalaya keep growing. Now when Himalaya grows, as I told you, that we have the endogenous processes that's called earthquake. Then the exogenous processes includes all the surface related processes. This surface processes gets into the hazards when you have the anthropogenic effect or human intervention. So that's how we call it as the natural hazards. So now you see life at the Uttarakhand actually. If you see the Himalayas, basically they don't have a land. Like if you see in Tamil Nadu, especially in southern India, especially in Tamil Nadu or any other states where there is no mountains, even if you have a mountains, they are all relict mountains. They're all old mountains, Vaisana mountain. They're all old people, just like in geological features, they are just like in old mountains, like Western Ghats and Eastern Ghats. But those mountains were like this Himalayans previously. So, but now you look at the mountains of Himalayas, as I said, that they are growing at a rate of 6 millimeter per year. So they don't have any flat land actually. The flat land is only available very close to the river on either side of the river bank, or they have to locate themselves somewhere in the ridges. So when I visited sometime in 93 in Uttarakhand, most of the villages all settled on the ridge of the mountains, or not much hazards happened actually. But now because of the urbanization and the kind of more socialization, and everybody wants to visit many pilgrim places, or they want to hike the mountains. So I don't know what kind of development has taken places that leads to lot of infrastructure is developed, but which is also really required, because in the mountain state people also need all kind of infrastructures, because they are also like a people, because they live in mountain, but does not mean that they cannot have such kind of privileges. But still that Himalaya has a lot of resources, not only giving the water to the plain people, but also it has an enormous potential to get all kind of resources. So essentially they don't have much space actually. You can just see the whole Himalayas will have this kind of say 2 to 3 kilometers valley width, and mostly people somewhere sit on the either side of the valley, and the river is flowing on this way. So they generally occupy some of the many the tourist vendors or any kind of an ashramam. They all built on the overbank of the river. The overbank is nothing but where the river can flood at any point of time whenever the river gets fully charged. So that's why we see such kind of an informations in the Himalayas. Now, if you see the next one, that's about the glacier. So glacier has been spoken by Shankar. So it's, in fact, glacier is nothing but the thick ice mass actually. So it gets recrystallized, the snow is get recrystallized, and we have the two type of glaciers. We have the valley glacier and we have the ice sheet. So ice sheet is nothing but the Antarctica, that's the South Pole and North Pole, we have that. So valley glacier, that typically just like it is in the mountain, like in Alaska, you can see that's a beautiful glacier is coming all the way on this side. Basically, we have the lateral moraine on either sides. So this is the accumulation zone. You can see in the Himalaya, we have such beautiful glaciers. It comes. This is what the maximum snow accumulation takes place somewhere here, and slowly this glaciers comes. Now you can see there are some small glacier on either side. You will see in subsequent slides. On a Google image, you can view like this. So basically the glaciated valley, it shows the U-shaped valley basically. You can see that this white ice, they travel along this. Basically, that's how the glacier moves actually, that you can see in a small cartoon on a next figure. You can just imagine that this is what the accumulation of the snow takes place during the winter. Then the permanent ice will be there actually. So this is called the accumulation zone, especially on a valley glacier or an alpine glacier or a mountain glacier. In a case of a plain glacier like ice sheet, we have the Antarctica or Greenland, they are the examples. But in the valley glacier, we have the accumulation zone where the snow gets permanently frozen and they become very, very, very hard ice actually. Now, but when these glaciers moves, then they get degraded. That is called the zone of ablation, damage our zone, that is a glacier. But if you see that, you just imagine that the thick snow of continuous pile of snow gets accumulated over the bedrock. This is called the bedrock. Bedrock is nothing but that basement in which the mountain is formed actually. This is what this contact basically. Now you can see that the snow has its own weight. Basically the potential energy is more.
Sir, you have muted your... Again, you.
Now I'm audible?
Now you are audible.
Yes. Yeah. So previously also I was not audible?
Just for the last 10 seconds or so. I mean.
Okay, maybe I can go back to the previous slide then. So in the glacier, basically in Himalayan glacier, you can see that I said that there's higher Himalaya, that higher mountain peaks just above the 3.5 kilometer contour height. That's the elevation from the sea level. The mountain peaks are permanently frozen actually. So there you can find the kind of a valley glacier. So that's the beauty of the Himalaya. So if you see in the next slide, how the Google image it looks actually. So the glaciers in the Himalaya, they form a U-shaped valley actually, because the glacier really moves. Glacier will move based on the topography, because you can see on the next slide, the topography of the glacier, and this glacier with respect to the topography and the bedrock contact basically. You just imagine that you just remove all the snow. You just imagine this is the bedrock, and you keep accumulating the snow for several years. Then what will happen? The snow will continuously pile up and it become a black ice. So it becomes frozen. And another season, new snow comes, and slowly there will be a temperatural variations. Due to the temperatural variation also, sometimes the snow avalanches happens. So there are variety of snow avalanches, internal avalanches, external avalanches, but I'm not going into the detail of on those. But if you look at these things, you just imagine the glacial based on the topography. Basically, this glacier moves because of the topography, because of the weight, and based on the heterogeneity between the bedrock contact and the glaciers. And within doing so, the glacier also forms the kind of crevices. It creates some kind of fractures. Basically, wherever the snow is moving, because of the movement, it forms several crevices, like a marginal, transverse crevices. There are variety of crevices happens. They're nothing but that fracture. Glacier pilau pattu poradhu. So in the accumulation zone, you have the always snow is accumulating, but the dynamic zone is the ablation zone basically. So here the glacier melts, sometimes it goes back, sometimes it goes further forwarding to the motion. If it more forwarding the motion, that means Imayamalai or glacial வளர்ந்து கொண்டிருக்கிறது. இப்போ பின்பக்கம் போச்சுன்னா, if it goes behind, then the glacial is retreating. Then like Professor Shankar, they will say that's a climate change. You see that this much 100% or 20% there was a climate change because of the carbon dioxide increase. There's a global warming. So all these things are very fancy name as being introduced. But when you see, look at that, we have to also understand that these glaciers, when they sit on the basement of the bedrock, it has a tendency to move because of their basement geometry. And also we have to take into the consideration such kind of research has not been done in the Himalayas especially. And also we have to maintain some kind of a radar observation how this glacier forms. In fact, we did with Mont Blanc in alpine glaciers, we continuously monitor the glacier movements. So that's number one. Then in the just in front of the snout of the glacier, you form some kind of an iceberg formed. Like in sheet glaciers, basically glacier will get degraded. That is a different phenomena. But in this case, in an alpine glacier, you form a lake. Then sometimes this lake got busted and they then damage the downstream valley also. So glacial, you just imagine glacial as a powerful processes. In fact, it can crush any kind of a rock basically by different processes called the plucking and abrasions. So it can really damages the rock like anything. So you don't need basically to have too much of water or too much of energy. Basically, you need some kind of a triggering factor to just slide some kind of an ice blocks that can do the miracle with the help of the debris flow. Debris flow means nothing but that man, kaliman, all kind of material, just they amalgamated in all kind of things. If they have some kind of a small amount of water, that's called, we say, debris flow. With respect to the slope, it can do the very devastating damages. So now just imagine on the previous slides, if just imagine, now you forget about this glacier has moved back. Now in the glaciated valley, there are mountain glacier, where everywhere there will be some kind of a glacial accumulation will be there on the just circuit portion. That means that the deepest part of the mountain glaciers. But just imagine that this glacier has moved back. So then what you will see basically, then this is what the glacier has been evacuated and they gone back. And because of that, there are some deepest part of the glaciers still there. It will have the kind of an hanging valley. So just imagine. So that means there some places the glacier is evacuated and some places will have a glacier. And these small tributaries, they try to make a very, very narrow kind of gorges. You can see if you have gone to the higher Himalayas especially, you can see basically just on a cross section of the butter, you can just, this is on a butter, you take a small knife and you can cut this kind of a section. This becomes your road or a river. You can find out that's a deep narrow gorges. You can see just north of the Joshimat. If you drive just north of the Joshimat, so you can find out the very narrow gorges basically. So there you can find out this kind of the hanging tributaries in which some of the land masses is on its upstream, it has some kind of a snow glacier or whatever things will be available. So that's the very important point that you should remember here, is that there are some hanging valley glaciers. That's the terminology is being used in glaciated valleys. There are many things. This is the circuits. So I don't want to explain that. This is the characters we are going to discuss. That's what I'm just giving an introduction on that. So now you can see that in Himalayas, this is what the HG hanging glaciers. You can see that's a beautiful hanging glaciers. Then this is the small river valley, and probably you see, you can just imagine the height differences. You see, this is another valley, and this is what the height differences. Just for your estimation, I'm just giving. So now, as I said, that the glaciation, that the reason is the plate tectonics and the Milankovitch hypothesis, it has already been discussed, so I don't want to elaborate much on that. Okay, now, so first we discussed about the Himalayan tectonics and life at Himalaya. Then the third point we discussed about the glacier and glacial features. So what happened to the 2013 actually? That's what the people say, that's a glacial lake outburst. So we were there as a part of the Department of Science and Technology initiation. That's a Mannu mapping of neighborhood in Uttarakhand. So this is the Kedarnath temple. Actually, you can see this part. And this is what the Chorabari Lake actually on this backside. So what had happened actually, I said in the previous slide, that is a supraglacial lakes, some kind of a lake was formed and it got breached and it came all the way through this, that's the Mandakini River, and it washed away most of the town or most of the building or houses constructed on the overbanks. So that's the story. Now what we will see that just we'll see this, the background of this Kedarnath Mandir, you will appreciate how strong the natural surface processes. These are all the huge boulders basically, and they came from this this particular elevational differences of particular distance. This is what the distance between this lake and the place, and you can imagine how furious this big boulders basically. Now I will further zoom in. Actually, this is the Kedarnath temple. Just imagine this on either side of the Mandakini Valley. As I showed you in the previous slides, the glacier moves, it will have the lateral moraine on either sides, and then it makes a U-shaped valley. So this is a basically outwash plain actually, this Kedarnath area. So this Kedarnath temple has a long history. In fact, Adi Sankaracharya in 6th century has renovated this temple, actually Kedarnath Mandir, and that kind of an evidence is also there in Kedarnath temple. So you can see that just very close up, that's about 11-meter big rock actually. This is a granitic rock actually. This is 11-meter long actually. In fact, this rock very interestingly, it protected this temple. In fact, you just imagine when this rock is not oriented like this, then this whole boulder would have washed away all this Kedarnath temple. So that's the miracle basically. That's the geological processes. Because see, the boulder will have the kind of an saltation kind of a pattern. Basically, it sometimes rotates, sometimes it will go along with the long axis of the boulder, sometimes it go with the intermediate axis of the boulder. So we studied all these processes, but still we can always think that this is basically a miracle. So this 11-meter huge boulder in fact protected this mountain. So what we did in Kedarnath tragedy, after the tragedy, we went and we investigated these areas. We wanted to understand that probably, see, now people started worshipping this big rock actually. So that means the same thing would have happened in some time back. So what we did that now when further we examined this, I think some slide is missing. Okay, now let's see. Okay, so we wanted to also understand the paleoglaciation on either side of that Kedarnath Mandir. So we also started doing the kind of a surface exposure dating, and we used all kind of a survey to just measure the height. So, but now you can see from the one side of the ridge, we could see the Kedarnath temple somewhere here it is. So this is basically a bar deposits. What we say bar means, the river வந்து நடுவுல இருக்கிற island மாதிரி உள்ள இடம் தான் அது bar. So river வந்து இப்படி போயிருக்கும். So it's a kind of a bar deposits. That is what we see from this photograph. So now how you can see that the whole area got damaged, and on the bank of this river, many of the houses has been built is totally collapsed. Now you can see that what we have done, as I told you, that we wanted to investigate this time also that Kedarnath temple got distracted. So what we did that using the collaboration with the archaeological department, we just dated this binding material. And also we found there are some kind of a junk of charcoal people they used for burning the firewoods, all these things were there in that particular surfaces. So that means that some cultural activities happened. So we try to date those things, and we wanted to understand the kind of any kind of a disaster or anything happened. That is a different story. Basically, what I wanted to say that this what is the repeatability of this disaster? Like we have already introduced the time scale actually. So we want to also understand that what is the cyclicity of this hazards or cyclicity of the any kind of an glaciation or interglaciation. So such kind of study we were interested on that particular time. So now we know that we have seen that glacier and glacial lake outburst flood that can also give the disaster, and now we'll see the landslides basically. So this is the landslide which happened in 2014 in Udhampur district in Jammu Kashmir. You can see the land get slided, land get, அதாவது அந்த காலத்துல ராமாயணத்துல எல்லாம் சொல்லியிருப்பாங்க வந்து பூமி வந்து பிளந்துருச்சு அப்படின்னுவாங்க. So this is what happened actually. இதுல எப்படி ஆச்சுன்னா, this is how this landslide has happened basically. Extreme rainfall, and all of a sudden we have the what you say that cloud burst, basically more than 100 millimeter rainfall for an hour. It will give such kind of thing, provided that area should have the kind of a lithology in which the rainwater can wash away that lithology. For example, களிமண்ணு மண்ணு அந்த மாதிரி சேர்ந்து கல் இருந்ததுன்னா, sometimes just you can imagine that there is a bedrock and we have a clay that's incompetent. This is the bedrock that's a competent. Sometimes this clay get washed off. So if you have such kind of a lithological exposure, this is what the beautiful example. If you go to the Vaishnavi Devi temple in Jammu Kashmir area, you will see the red color rocks. That's a murri rock we say. So it has a combination of the bedrock with the hard compact sandstone with the mudstone or a clay stone. So it get diluted, washed away by the rain. So that resulting to such kind of an huge cracks on the top surfaces. Basically, as I told you that in the mountain state in Himalaya, we have alluvial cover. Say sometime depending upon the places where the alluvial cover, it varies from say few meter to sometime it goes to kilometer in a Indo-Gangetic alluvial plain. So that's why when we have a different rock type, then when it gets washed away, then some kind of an instability happens, then all of a sudden the landslide forms. So you can see the beautiful ground fissures basically. So this is a closer look how this rock debris basically, when you take the landslides, then how this looks basically. This is what it shows, that this is the landslide scarp. This is the ridge of that particular mountain. It's a zoomed one. That's a back portion. You can just imagine the distance is, it's almost more than 300-400 meters basically. So it's basically a rock debris. Now you can see, I just further going in a different scale of the photograph. You can see there's another big boulder, and you can see the shallow landslides, and this is what the big ridge, the incident which took place on the just behind this spot. So that means in Himalaya we have the landslides. This is very frequent phenomena. So the landslides, this could be related to the extreme rainfall event, related to the topography and also lithology. So these are all the some of the things which really affects the landslides. Now there are big challenges because we have a such kind of growing mountain. We have to develop the infrastructures for not only to develop the mountain status people, but and also we wanted to pull out some kind of resources. It's a big challenge for the civil engineers. And also we have the bank erosions. I told you that the river valley is about only 2.5 to 3 kilometers width, that have a limited space. So basically even the Uttarakhand government has strictly enforced that just close to the river banks, no such kind of building should be erected. But still we don't have any kind of spaces, but this is what people live with this kind of a problem. Now coming to the Chamoli disasters. So what could be the reason basically? Now just closely look at the Tapovan project. So that is located in the Doli Ganga river. So in this disaster, there are two projects. One is the Rishi Ganga project on the upstream of this Tapovan projects, and this is the downstream. So you can see there's a marker horizon I marked in a discontinuous circle that's in a house. Now the flood actually you can see in a subsequent slide, and also during the Kedarnath tragedy, so we also measured the level of the depth flood extent actually on a one dimension, basically depth level, basically how far the depth the water flood or the flood came. So that also is very important. So this is what the before the disaster happened. Now if you look at the disaster Batme, after that this totally this whole infrastructure has been totally washed out actually. Now if you look at the geology of that particular area, that's called the Doli Ganga. This is what the Tapovan is, that the previous slides located somewhere here. This is called the Doli Ganga river actually. Then this is the Rishi Ganga river basically. In rainy actually these two rivers basically, this Rishi Ganga meet with the Doli Ganga, then it becomes Alaknanda river on downstream. So now you can, what we will do is that in the couple of slides, we will see the downstream geology and geomorphology of the upstream. So that is what so you can see that. Hello? Yeah, this is what the initial scientist has given, that something landslide happened with an elevational difference of 5,600 meter to 3,800 meter, and with a lot of dust, and it blocked that Rishi Ganga and eventually got flooded. So that's what the one theory says. Then subsequently they showed some satellite images with a lot of dust and all these things. So this is what the rainy villages, and the glacier broke somewhere here and it blocked the Rishi Ganga. That's what the first initial climb by the foreign scientists. So now you look at upstream in Ganga, it is totally white mountains basically. Now if you see the further upstream, you can see there are a lot of sediments. It's a Google image, and this is what the landslide scarp has happened during that event. And you can see there are huge material, and with the bedrock basically, I told you that. So bedrock above which the glacier sits, and probably this could be a hanging valley glaciers. Probably there was a fracture probably happened like that. But before that, you can see the lot of materials are already available on the valley floor of that river actually. That's the Rishi Ganga river. That is what the important observation you should see. You can see on either side that huge amount of materials are there on the river valley, fine size sediments basically, like glacial deposits, or we say that tillite deposits or glacial deposits with the fine sediments is there already available on the valley. Now you can see the downstream just south of the rainy village, you can see the geomorphology of that area. You can see that's a narrow valley I was talking. This is the Rishi Ganga river. That's a rainy bridge. Now you can see further down, this is what I was talking about, the deep narrow gorges where these two rivers meets, and the Doli Gangas goes further south, or Alaknanda it becomes. This is a rainy part. So you can see this is what the plain area, people have the houses settled over here on the terraces. This is what the normal downstream of this Rishi Ganga. So what happened actually, basically this is the report from the ISRO actually. They use the satellite imagery and try to understand the hazards basically. So this is the Rishi Ganga river. You can see from here, this is the Doli Ganga is coming, and this is the Rishi Ganga. They are meeting at Raini, and this is what the Tapovan. So we had a power project one, hydropower project at Tapovan, and in the Rishi Ganga, that's a small hydropower project. So basically, you see in a topographic, high topographic area, so the topographic gradient and water makes that very highly important for making the power generations, because after all this is also required to develop the mountain state. So that is also part of the developmental activity for the Himalayan states. So Joshimath is somewhere here. Now you can see during that time the mean precipitation, that's a snowfall variation. I told you at the beginning that there is a orographic barrier here. Rainfall takes place on the higher altitude just above the 3.5 kilometer, you will have the only snowfall. So just imagine that snowfall variation takes place between the 30th December to 8th February. You can see there is a considerable variation on the snowfall. So like one of the reasons people talk about the avalanches, if you have the continuous snowfall, then also it triggers the avalanches, because as I told you at the beginning that there is a temperature gradient differences between the already frozen snow and newly downpouring snowfall. So that can also trigger some kind of a fracture. And besides that, there are a lot of fractures forms on the glaciers, especially on the zone between the accumulation and deflation zones. So these are all some of the points we should keep in our mind. So that means the data says that there is a variation of the precipitations or a snowfall variation that's happened, and also some spikes between the 3rd February and 8th February. It's all very initial data set. Now you can see there is a temperatures actually. There are some temperature variation taken place between the -3 degree to and plus 4.85 degree. This is what we can see from between 2nd February to and 7th February. So this is what the ISRO people have studied. On 6th February, you can see this blue color is the snow cover, and this much snow has been evacuated. You just imagine that this is the valley. Basically, I was talking about the glacier. That's a mountain glacier, means every slope of the mountain, there will be a accommodation of some kind of an ice. So that means you can just imagine on that particular catchment, especially on a Rishi-Ganga, this is the snow cover, and this how much snow has been evacuated on the 8th February. So you can imagine how much snow has been pulled off basically from that particular hanging valley, or maybe any kind of an peaks. So now you can see that this is what basically the fresh snow on the pre-event 6th, and this is what the post-event on 7th February. You can see I already marked that's Doli Ganga and Rishi Ganga and Rainy, all these things. So something happened on this particular spot. So that's, you can see on that's a dust plume zone of 14 square kilometer area actually. So what had happened actually, you see this is what the Rishi Ganga main valley. As I told you beginning, there are some glaciers, hanging valley glaciers. Probably something has happened on this, and it has totally, all of this material has been evacuated. And now we should ask very important questions. Now, maybe coming to the next subsequent slides, I will also ask you that we don't have any kind of an lake formed and subsequently it got breached off. In fact, it is in a continuously, this whole thing is got evacuated because of already the valley floor had enough sediments, and it had a lot of mountain ice and other things, basically formed a very big debris flow. And the moment it reached to the Rainy, where it caught the water, sufficient water on the Doli Ganga, then it picked up actually. So that's how this incident happened actually. Now you can see that this scientist from the ISRO, they could do some kind of a modeling. What was the water level at the time of the flooding? So since it's a single river network, they could do the modeling very quickly, because basically it's a one-dimensional model. So they just suggested that 24 to 15 meter actually the maximum water went up. In fact, during the initial slide I showed you some water actually. I don't know, because that what is the exact height between the valley floor and the house is located. So the maximum extent of the flood depth, basically, that's what we see in the Kedarnath tragedy also. It never gone that much height actually, but it all depends where exactly in which part. So generally these scientists predicted 24 to 15 meter, and near the Joshimath it went up to 1 to 2 meters basically. So this is what their fundamental pictures basically. I'm just skipped. So this is what they were suggested, that some kind of a fracture happened and it just broke off this glacier. Subsequently that incident happened. So this is what the aerial survey, this is pre and post. Now you can see the whole Tapovan actually that hydropower got totally damaged out. Now, if you see the aerial survey by our institute actually, so they visited soon after this incident, and they could find out that that is called the Rauti Glacier. It's called the Rauti River. I told you there are some tributary. So many, this is a mainstream, many tributaries contribute to form the main stream. So similarly, imagine in a glaciated area, we have the glacier on a main glacier. On a small tributary, we have a small glacier. So tributary glacier. So on a similar fashion, that kind of Rauti glacier, Rauti rivers, so something has went bad or something, some fracture happened, and in fact it has totally evacuated and it just blocked it whole of the Rishiganga river, and it collected the water and probably damaged the things. This is what the aerial survey says. Then this is what this basically, there's some crack on the glacier, and then immediately it break off, and it can, in fact, it can go very fast. As I said, that the glacier will have a powerful abrasion and plucking, all these effects, and with the debris flow kind of an deposits, it can pull out all the material, and it can damage the whole of the valley which is on the downstream. So that's what we could see from the aerial survey. Now this dam lake is happened actually. This is a post disaster. But when the disaster happened, we do not know whether we had any kind of a dam lake, like many of the scientists, they were speculating at the time of the incident happened, that could be a glacial lake outburst. But in fact, we don't have any kind of a supraglacial lake was there and it got breached off. So we don't have such kind of an information. So basically, this is all happened because of the landslide and avalanches, because of the hanging valley glaciers broke off, and due to the debris flow deposits, and it vanished all of the downstream basically. So that is what the climax is. Now you can see that this whatever the water has been dammed out, it's coming slowly. This is the post scenario. So this is what the Rishiganga project on the Rishiganga River Valley. The Tapovan is further down south of this Doliganga River, where the NDRF team is working on that. And this is what the Tapovan project, you can see that this is totally washed off. And also I would like all the students especially to enroll themselves in Indian science. This is the initiative of the DST. They can find out all kind of videos and all kind of scientific subject for all the discipline, basically for mathematics, physics, chemistry, biology. So I request all of you to kindly download these apps in their mobile, so that they can enriched with some more scientific knowledge. And I think that's all from my side. If any kind of doubt, in fact, today I did not able to mix both languages because already the professional speaker, he introduced in a very professional way. I was also followed in the same way. And I thank you.
Okay. Thank you, Perumal. It was a fantastic talk. And I'm sure a lot of questions are already there in the chat box. Probably Vijayan, can you run through the chat and post the questions?
Sure.
Okay. And in the meantime, probably you can also check if somebody is raising hands.
Okay.
And give them permission to ask questions. Now you can go through the chat.
Okay. We go through from top down.
Yes.
The first question from So the question for Professor Shankar, it's from Aditya Verma. What is the impact of methane versus carbon dioxide on greenhouse effect? The second question is whether it is true that the impact of greenhouse effect in present time is a blessing in disgrace, or as it has prevented delaying the onset of next ice age?
Well, firstly, both methane and carbon dioxide are greenhouse gases. Both of them are present in the atmosphere. The what do you call it? The modeling shows that the carbon dioxide really controls and is a more dominant feature than methane. But both are greenhouse gases and both are there in the atmosphere. Now, I think, greenhouse effect, stopping the next ice age is not an issue. The greenhouse effect has always been there and ice ages have always been there. But the greenhouse gases do make life comfortable for us, in the sense that if you don't have the greenhouse effect, the average temperature of the earth would have been something about 30 degrees lower than it is now. Right now, it is some 14, 15 degrees centigrade average throughout the globe. If you didn't have any greenhouse gas, if you didn't have the atmosphere, this temperature would have been some minus 20, minus 30. So, the greenhouse effect does regulate the temperature of the earth. The problem is more that if we are pumping in so much that it is going out of control and heating up. Now, next ice age, the ice age phenomena are at hundreds of thousands of years, 100,000 years, 40,000 years, 20,000 years cycles. So, what is going to happen in the whether human activity today is going to affect ice ages, the coming ice ages, very difficult to say. We cannot predict the system so much in advance.
Okay. So we'll go to the next question. This is from Mohammed Ismail. Change in past temperature from glacial to interglacial is abrupt, while interglacial to glacial is gradual. Why?
Yes, so I saw that question. It's an interesting question, and I don't know the answer. I mean, that curve is not symmetric, and I don't know.
Someone from the students should do the research, right? Lectures in the current subject.
Yeah, it's a good observation, but as I said,
Dr. Vijay, and maybe I will address it afterwards, probably once Professor Shankar complete his
Now, we have only 2 questions in the chat box. I think Shanta Kumar Muttu, he has raised the hand. So he can ask the question, then we'll move to your place.
Okay, because the change in past temperature from glacial to interglacial is abrupt, while interglacial to glacial is gradual. See, I don't know what Mohammed Ismail basically wanted to say that. See, I told you that the natural processes, basically, it's the final outcome would be the instantaneous, basically. That's the abrupt, actually. See, if you take any kind of thing, see, now what we are seeing is basically a small time scale, actually. Like Professor Shankar has elaborated very nicely, introduced the different time scale, actually. Now we wanted to understand the natural processes, at least in our human time scale. You can talk many things like what is the impact of methane versus carbon dioxide greenhouse, like any kind of published report in Science or Nature. There is a sudden spikes, basically, especially in emission of carbon dioxide and other thing. Now we do not know, because the Earth has a own self-sustainable system. As a geologist, so we should not panic the society, basically. We do not know on what time scale each of these proxies or each of these variables varies with different times. We have no idea. That's why we wanted to understand the geological processes at a different time scale, like probably like Professor Shankar, they work on an instrumental time scale, say maybe 50 years or 100 years. Like a geologist, somebody will work in, say, in 10,000 years, and somebody will work on a late Pleistocene scale. So each of these scales, if you understand the natural processes, so then only we can discuss about this kind of the questions, basically. But nothing is basically abrupt, basically. So any kind of the climax looks like an abrupt, basically. Now, for example, we all know that the whole crust, basically, that's the lithosphere, it accumulates the elastic strain. That all we know that Indian plate is deforming, and also we know that Himalaya is growing. So it is continuously accumulating the elastic strain. then at one point of time, like it reaches some kind of a critical threshold limit where we do not know that magic limit, then it turns up into some kind of a disasters. So similarly, like a glacial and interglacial cycle also, there are many different small cycle. Like we do not know that it was a last glacial maxima has been spoken, but we had a little ice age after that. So we have no kind of a systematic time gap between each of these cycles because we do not know. So that's the question actually. Even if you take the glacial code, you cannot go more than say 1,000 years or 2,000 years, or maybe maximum you can go about 10,000 years. But again, it's a site specifics. So we cannot come to such kind of a direct thing saying that something is very abrupt, something is gradual. And that's the answer for the both the questions actually.
Okay, Siddhartha Muthu Vijayan, can you unmute it before you ask the question? Yeah, we'll go to one question and you can ask your question later. One question. So, what is the causes of ellipticity of the orbit to change? This is from Chitra Narayan. This is to Professor Shankar.
Yeah, if there had been only the Earth and the Sun, then the orbit would have been a perfect ellipse, unchanging ellipse. But there are other planets around which also exert gravitational pull on the Earth. Mainly Jupiter is the main dominant thing. So these changes in the orbits are basically due to the effects of the other planets in the solar system. So then it's no longer an exact Kepler problem which one does in school. It's a complicated dynamics actually. Many bodies, there are about 7-8 planets, they're all interacting with each other. All these changes in the orbits are due to that.
Okay, thank you. Siddharth, can you go ahead and ask your question?
Yes. Actually, it's not a question. I would like to share an additional information on the glacier burst, what happened recently in Uttarakhand. I came to know that on the same day that when that glacial burst happened, now ISRO actually, it says that it is associated with a landslide or an avalanche kind of a huge glacial mass fell down at the height of the height difference between the valley and the hanging glacier was around 3 kilometers roughly. This fall was recorded in a seismometer somewhere near Mussoorie by NGRI. And the sudden peak, that acoustic energy released, it was estimated that it was equivalent to a 3.8 Richter earthquake. That was an initial report. Just this is an info to Professor Jayangonda Perumal.
Actually, I'm aware about that actually. In fact, Wadia recorded that. Actually, see, I did not share those things because it's a kind of an ongoing research. So I don't know. NGRI, see, we have the station and the NGRI also have the stations. In fact, see, most of the such kind of interesting phenomena we correlate after that. I thought that I should not disclose those things in the common scientific forum. Actually, it's because I'm representing the Wadia. So
okay. Just out of interest, because in case if it is not, you could have checked with Wadia Institute. That's
I'm quite aware about that. I'm interacting with this, but now actually I will put this way also. See, what was the magnitude? What is the noise basically? You see, people all argue about 2.5 square kilometer area of junk fallen. We have no idea absolutely. See, why do you want to exaggerate the things? Nobody has witnessed. We have not even gone to the ground truth actually. We all went up to Rainy. That's a village where we can go. Professor Shankar probably might be there, where that place where you can see. We do not know. It's all speculation. Well, how much the big, huge block has been fallen. We have no idea, absolutely. So that's what, as a scientifically, I'm talking about that. Yes, Professor Govindarajan wanted to. Yeah, please.
Okay, since you are talking about some kind of a conspiratorial tone, there was one report about whenever something happens in Himalayas around this area, there was a report that in Nanda Devi, about in 1965, there was an agreement between CIA in US and Indian government to put a plutonium device so that they will monitor what is happening in China. And it was never put there because of some collapse which took place, and it has been left there by the expedition, by Mr. Cowley, if I am right, the famous trek, this thing. And there is always a claim when something happens, there might be some trigger from that kind of a device which was put in there. This is essentially conspiratorial. There is no evidence for any of these things. Since you are raising this issue, I can also mention that.
No, that's what actually.
But by the way, this landslide is on the Trishul mountain, not on Nanda Devi.
Yeah, that's true.
So Nanda Devi is far away from, I mean, about far meaning probably 30 kilometers or so away from there.
Okay.
But actually, Professor Jayangonda Perumal has shared some temperature increase. So may you know what is the source of the data? Is it in situ observation or is it satellite based?
Which one, sir? About what? I don't understand.
Hello, am I audible?
Yes, yes. Go ahead, please. Again, say it again.
No, there is a sharp increase in temperature during that time.
Actually,
can you hear me now?
Satellite data, in fact, that's available in ISRO. In fact, I got it from one of my senior colleague, my friend actually. So there already it is available in the ISRO website and also in the IRS. It's basically a satellite data. So that's what in my preamble in my talk actually I gave. I collected all the information from the AGU and ISRO and Wadia and my personal experience in other terrains. So that's how this has been done. So it's all basically based on the satellite data set.
I think he's asking about the temperature data.
Temperature
and precipitation.
Temperature also they have utilized from the satellite data only, because some people have the AWS in Joshimath. I don't know whether they shared it with them or I do not know, because in Himalaya nobody share the data, so I have no control on that. So basically it is the report made by the ISRO people actually. So probably I guess there are some places we have the AWS, even Wadia Institute we have the AWS data set. In fact, even I was not given those data sets basically, because the glaciologists, they will make use of that data sets. Just for this talk, I just compiled it and I gave.
Okay, so we are overrun our time by 11 minutes. It's the time to close it. When we don't have any further questions, it's better to close it now. I have two appeals. One is we have provided the link for your feedback. Please click the link and fill up the feedback form. That will help us to improve our programs. The second one, I have seen this in the last 10 to 15 events. We have a different set of audience depending upon the topic we are dealing with. That means it is slowly polarizing into the subject that we are dealing. So I would like everyone to become a member of our Telegram group that we are posting our events regularly. If someone is interested in the event that we are conducting, they can participate in the meeting or the event. So I would like you to click the link and become a member of that the Telegram group. We also have a Google group. If you are sharing your email ID, definitely we'll include you in the Google group as well. With that, now I'll try to close. We can close it, and again, our Chella Kumar can provide the vote of thanks, formal vote of thanks. Chella Kumar, are you available?
SP Salakumar?
Yeah, it's not.
Yes. Sir,
no problem. Okay, we will close it as on behalf of PSL. I would like to thank Dr. Shankar and Dr. Jayangonda Perumal for their excellent lectures. It's really a very great lectures and everyone enjoyed the lectures. And we'll see that now we have provided all the recorded version in our YouTube link. Popular Science lectures. That is we have a separate channel for YouTube. You see that all our lectures are being viewed by nearly 200 to 400 people. So this will be viewed within a week, and I hope that it will be viewed by at least 200. It will hit more than 200 to 300. I thank both of you for offering an excellent lecture. I thank Dr. TRG to introduce the speaker nicely. I also thank our colleagues for organizing this meeting excellently. I thank Dr. Seduraman to provide an insight into the National Science Day. I thank Challakumar for starting the meeting. Thank you very much. I also thank all the audience be with us for more than 2 hours and patiently hear the lectures. Thank you very much. Thank you all.
Thank you, sir. Thank you, Professor Shankar. Thank you. Good evening, sir. Bye. I will collect your number, Professor Shankar, your number. I will speak to you later.
Okay.
Okay. Thank you.
Okay. Thank you all.
Thank you.
Thanks. Bye.